Hey there, and welcome back for part 2 of building Ripple. In part 1, we talked about the DHT11 temperature sensor, and we figured out that we could connect it to a microcontroller and use Rust to get some information out of it, like the temperature or the humidity. We also talked about GPIO, timing, and a few other critical hardware and software features that we can use going forward. Before we can start anything new, we need to have a conversation about the code written for part 1. As I was recording this video and started writing the code for it, I noticed some pretty serious flaws, both in terms of logic and timing, and I want to take a few minutes to discuss those issues and really delve into why they exist and the solutions that we have for them. In our code from the last video, we were reading each bit individually, assembling that into a byte, and returning that byte before we moved on to the next one. This worked initially, but as I began to clean up the code and started writing new features, I was noticing some more timeout errors from the sensor. I dove into this issue, and what I noticed was the sensor was actually sending data, but a lot of the data that we were receiving, especially towards the end, ended up being all ones. This also included the checksum, which is the final byte to be sent, and that can cause real problems because we need that checksum to verify the data. I dug further into this issue and I noticed that the initialization of the sensor was working fine, but reading the bits, there were small timing errors all over the place. This began to add up and eventually corrupted almost our entire data output. Now, I knew that the temperature sensor had been around for quite a long time, and that there were a lot of libraries that other people had written, so I began to dig into some other people's code and see if I could find a way to resolve the issue. In hardware, timing is everything. It's important for passing messages back and forth between different devices, and it's used in various protocols as well. Everything from wired protocols like USB to wireless protocols like Wi-Fi and Bluetooth, and even for tiny little temperature sensors. In fact, it's so important that there's a dedicated component just for timing called a crystal oscillator. This allows us to time keep in a very precise way and gives us additional features like adding delays in our code. But there's another component that we need to consider, and it's actually our own code. It's a bit of a crazy thought, but every single instruction that we write actually takes a small amount of time. How much time isn't really important because it can vary between different crystal oscillators and microprocessors, but it is something that we need to consider. And there's actually a third element to this problem, and it's called an interrupt. When we're writing low-level code for embedded or even for our normal CPU, we can take advantage of a feature called an interrupt. Interrupts are actually a pretty neat feature, and they do serve an important purpose. They act as a signal to let the CPU know that something needs to happen immediately. This is good for something like a keyboard or a mouse, because when I press a key, I expect some text to show up almost immediately. Now, granted that not all modern keyboards actually work this way, but it does pose a significant problem. And that is when we're trying to do something time sensitive, like read pulses on a temperature sensor, we don't want any kind of interrupts. So we need to minimize the amount of code that we have that is time sensitive to avoid interrupts and other issues. Now, we understand the problem and clearly we need a different approach. But this sensor's been around for a while and plenty of other people have used it, so surely a solution must already exist. And in fact, it does. Adafruit has already written a library for the Arduino, and with a little bit of translation from C++ to Rust, we can use some of the same concepts. We can see in this library that a lot of the timing critical code is actually written to happen all at once, and then we can post-process it later so that we can actually get some usable information out of it. So let's take a look at the revised code and see what concepts we can learn from our translation of the Adafruit library into Rust. As we can see here in the revised read data function, we're essentially still initializing the pin the exact same way. We don't need to make a change here since that was still working correctly and is essentially what Adafruit was doing. We do have a new expect pulse function, but since we use that multiple times, we're going to hold off on looking at it just for a moment. And now we come to the biggest change. We start off by creating an array of 80 elements, and we use that to hold our pulses. We're using a little bit of Rust magic known as an iterator to manipulate this loop. And if you want to understand better how iterators work in Rust, I will leave a link to the explanation in the description. What's important is that once again, we used expect pulse, but this time we store the return value in the array. Why? Well, let's take a look. Expect pulse looks kind of similar to how our conditional read pulse function worked, but rather than passing a closure that allows us to check for whether a pin is high or low, we pass an expected level, and we perform the check inside the function. We then enter a while loop, which is similar to what we had before, but this time we're actually keeping track of how many times we've gone through that loop. We still do a check for our timeout, but at the end we're returning the number of times we've gone through the loop, so long as it doesn't exceed our timeout. This count is what we're storing in our array of 80 elements. And as you can see, we do this twice for both a low and a high pulse, and we store that as a set of pairs. This makes more sense when we look at the datasheet. We can see here that, based on the timing diagram, we're essentially taking advantage of the pairs of signals that we see here, one low and one high. Adafruit's library mentions in a comment that each bit is actually sent as a 50 millisecond low pulse, followed by a variable length high pulse. We can see that that's the case here. If a 1 is being sent, the high signal is sent for around 70 milliseconds, and when a 0 is sent, it's much shorter, around 25 milliseconds. And as we can see from the full timing diagram, these can be thought of in pairs, which, as we said before, is exactly how we're storing them. And critically, this allows us to reduce the amount of delay we were implementing before. Instead, we take advantage of the delay a while loop gives us while each instruction processes, and we're waiting for the signal to change its state. Now that we've retrieved our pairs, we can do some work to post-process them. As noted here in the code, our critical timing functionality has been completed, and if an interrupt happens or we need to pause execution, we don't need to worry about the data being corrupted because we already have all of it. This is not unlike reading into a buffer. We receive the entire message the sensor has prepared for us, and then we do something with it after we have everything we need. In fact, the 80 element array is essentially just that, a buffer. The length of that buffer conveniently happens to exactly match the length of data we expect to receive. I do want to note that in an earlier version of rewriting this code, I did attempt to assemble the bits into a byte on the spot before trying to read the next pulse. Unfortunately, this didn't succeed because of the amount of time it took to actually return reading the bits, and I was still getting corrupted data a lot more often than not. I decided to abandon this approach completely and stuck with completely filling the buffer before attempting to process the data. One thing to mention, because I didn't talk about it in the first video, is that we actually use the most significant bit for the whole integer byte as a sign, the same way we would for a signed integer, even though it's not stored that way in our code. The processing that we're doing here is relatively simple, but it can be a little confusing at first glance because we're doing a decent amount of bit manipulation here. I'm not going to talk in this video about bit manipulation and logical operators, but I'll leave a link to a pretty great video about the topic in the description. Now, what we intend to do here is to iterate through each set of pairs. We're going to shift the current bit over by 1 first to make room for the new bit, and then we'll compare the length of the high side of the pulse to the low side. If the high side is longer, then we know the incoming bit is a 1, and we can apply the logical OR operator to set the current bit to 1. And if the high side is shorter than the low side, we leave the 0 that gets placed there. This is similar to our bit mask from before, but it's a slightly different way of achieving the same thing. Also, I'd like to point out that the index variable here is an unsigned integer and not a float. So when we perform this division, it will actually remove the remainder and round down, and we'll get the index of the byte that we want to manipulate. The rest of this process pretty much is unchanged, except for a little bit of additional code that I'll talk about in a moment. We still compute and verify the checksum as before, and we put the temperature and humidity bytes together inside of a float. Now, I take the time to stop and explain all of this because learning is important, and it's kind of the point of this entire video series. Timing is critical in hardware, but it can also be important in software. We don't see that very often because a lot of it is done for us in libraries and protocols and a bunch of other places. But when it is important, it's also important to be able to adapt and to be able to look up good references in other people's code. We want something that is solid and reusable, and we want to create it well. Now that we have a more accurate and reliable way of retrieving the data from our sensor, let's actually do something with that data. We don't really want to leave this thing hooked up to a computer all the time though. It's not really practical. And also leaving a terminal open isn't really practical either. So we need a way to show the information that we're retrieving. And typically when we want to show information from a computer of any kind, we use, you guessed it, a display. You may be thinking to yourself, but we don't even have a graphics card or an HDMI output. So how are we supposed to display our data? Well, those things are probably a little overcomplicated for what we need, and we can turn to something simpler. I have here a 6502 LCD display, and this is another older piece of technology that's a little bit simpler. I know this isn't what was originally in the design, but it gives us a good starting point for wanting to actually display our data. The 1602 LCD display module is actually pretty common, and it's been used in a lot of different applications. It gets its name from how it displays characters, 16 columns by 2 rows. We'll dive into the datasheet a little bit, but we're not going to need it nearly as much for timing and pins the same way we did with the DHT11 temperature sensor. This is because, just like libraries in the software world, the hardware world has multiple ways of communicating, known as protocols. We're going to use a specific protocol called I2C. I2C, or Inter-Integrated Circuit, was released in 1980, and it quickly became one of the most popular ways to reliably connect multiple devices. Now, we're not going to go into all the details of how exactly it works, but we will cover some basics so that we have an understanding of what's going on here. Remember how our temperature sensor only uses one pin to send data back and forth to the microprocessor? Well, I2C actually uses 2 of them, and there's a very good reason for this. The first pin is known as the serial data line, and it essentially just serves the same purpose, to send ones and zeros back and forth. But if you remember, we had to do a lot of investigation. We looked at timing diagrams, we did some guesswork, and we had to figure out whether something was a 1 or a 0. Somebody clever came along, and they decided we were wasting too much time trying to decipher 1s and 0s. So instead, we added a second pin. This pin is known as the serial clock line, and it essentially pulses every time there's a new bit. This takes the guesswork completely out of it and makes it a lot easier for us to read the data. Now, I'm not going to go into more detail than this, but there's a great video by Ben Eater that I'm going to leave in the description if you'd like to learn more. Now, I should also note here that not all of these displays are equipped with I2C. Most modern ones are, but the original design had quite a few more pins, and so a daughter board was designed to be able to translate between I2C and these extra pins. Unfortunately, the extra pins are kind of out of the scope of this video, and they're a bit too complicated, but for our purposes, they're not really important. Now that we have a basic understanding of what we're trying to put together here, let's go ahead and attach this display. As with the DHT11, we still require both power and ground, and these are hooked into the breadboard supplied power rails. For the serial data and clock pins, we're going to hook those directly up to the Pico. While these do use GPIO pins, we actually need to use very specific pins. Because we plan to use I2C, a quick look at the Pico's datasheet tells us we're required to use pins designated for I2C. The Pico is designed this way because the wiring required to use I2C and other communication protocols we'll talk about later are actually tied to certain internal components that they must pass through. There's a lot of internal technical details, and if you're interested in learning more, I advise you to take a look at Raspberry's official datasheet for the Pico, which is also going to be in the description. Now, there's a reference website that we'll use to help us solve our problem of which pins to connect to. As we can see here, this shows us exactly which peripheral is connected to which pin and what kind of line it can handle. You can also refer to the datasheet for your Pico or specific microcontroller, but for the Pico, I actually prefer to use this website. Now, if you're paying very close attention, you might notice that there are actually 2 I2C peripherals on the Pico. I2C is actually designed in a way that multiple child devices can connect to a parent and can communicate over the same lines without interfering with one another. This is actually done through the concept of addresses, not unlike a mail or IP address. Each one is designated by an 8-bit address, generally set through hardware. We can see here on the back of this display on the daughter board that there are a set of disconnected pads. Taking a look at the datasheet, we can see that these pads can be connected to change the physical address of the device, if it's required. When a message is sent over I2C, every single device connected to this peripheral receives that message. But the message will always contain an address, and only the device with that address will actually process the message, allowing every other device to ignore it. Sometimes this isn't enough, however. There might be two devices with the same address, and there's no easy way to change that address. This is why two separate I2C peripherals exist on the Pico. They allow us to logically separate those two devices so that they don't interfere with each other. Or we may want to logically separate the device for other reasons. Whatever the case, we're able to attach to either I2C peripheral inside the Pico. For this project, I've chosen to use pins 21 and 22, attached to GPIO pins 16 and 17, using the I2C0 peripheral. Now, with the display attached, let's talk briefly about a few code changes I made while you weren't looking. One of the major reasons I chose to use Embassy to handle the task of programming the Pico is because it falls into a class of software known as real-time operating systems, or RTOS. There are many great libraries out there that implement RTOS concepts, but Embassy seems to take a more minimal approach. It also has great support for other microcontrollers out there, so even if you don't have a Pico, you can still run this project with very minimal changes. An RTOS provides us several distinct advantages that we wouldn't be able to get if we had just chosen to use embedded HAL directly, or even alternative crates that provide support specifically for the Pico. The first and most important is the ability to use asynchronous code. Certain operations take time, as we've already seen. RTOS crates give us the ability to execute these types of operations in a way that isn't difficult for us to understand. If you've worked with pretty much any language that isn't C, you've probably already encountered asynchronous code. There's a lot going on under the hood in terms of scheduling and execution that we never have to worry about. And using an RTOS gives us the same level of flexibility, even though we're not working on a typical CPU. An RTOS gives us an almost operating system level of ease when dealing with embedded hardware. And I don't know about you, but when I'm learning something new, I generally like to take things one step at a time. And anything that will hold my hand a little bit while I get used to something new is pretty welcome. Now, as to why Embassy specifically, it was mostly due to the fact that it is completely written in Rust and gave me the least amount of issues when getting started. There are a lot of other great libraries out there, but I found this one the easiest to work with. This is in large part due to the way Embassy allows us to organize our code. Things we want to do can be divided into tasks, and these tasks can work independently without us having to worry much about when they're supposed to run or when they should be interrupted for other more important things. We can think of a task as being dedicated to one specific job. For example, I've moved our DHT11 sensor code into a task, as we can see here. The only job it has is to run every couple of seconds and retrieve some data from the sensor, then push that data into a channel. This channel will then distribute it among other tasks, like our display, and eventually other things. Another thing I did while you weren't looking was to add and set up a crate called Assign Resources. This crate allows us to define specific pins and peripherals that we want to use, and logically separate them out so they can easily be passed into our tasks. Later on, we'll see how incredibly useful this can become, but for now, we just have two structs for each of our tasks, our DHT11 sensor and our display. This means that if we intend to use other pins for our display, we don't have to go around changing a bunch of parameters in tasks and in other places. All we need to do is change the pin identifier here, and we're all set. Additionally, we've defined two channels here and some supporting types to make things a bit easier for ourselves. The first channel is our LED channel. I added a small bit of code to turn the LED on and off while we're actively reading the DHT11 temperature sensor to give us a nice visual indication when data is being read. We also have a separate channel for our sensor data so that we can share this information properly between multiple tasks without doing a whole lot of work. You may notice there are a lot of generic arguments here, and while I won't go too much into detail, I would like to point out the last one in the list. We have two different numbers here, 4 and 64. These define how many messages a channel can contain at once. And in the event that one of our tasks gets stuck, the messages can still enter a channel's buffer and be received by the task at a later time. In the case of the LED channel, we don't care too much about missing out on some messages, and so our buffer is small. However, in the case of our sensor, we do care a bit more, because later on down the line, we'll be getting data from multiple sensors and sending that data out to multiple receivers. We'll also try to normalize some of the data by taking an average, so missing out on as little as possible is pretty important. One final note as an aside is that I've also switched out the Pico I'm using for this demonstration for a Pico W, which has an additional wireless chip on it. I want to use this later to allow me to broadcast data from multiple sensors around the house and be able to collect that data in one controller. I will absolutely be going over this process, but for now, all we need to know is that there's a bit more work required when setting up the Pico and turning the light on and off. And finally, we get to the fun part, actually programming the display and showing our temperature. Actually, this part is kind of easy, thanks in part to Embassy and the magic of I2C. As shown here, we start off by sending some data to the display. These messages are used to perform a few basic functions. Most of the configuration data is based off of a great blog post I found by John at Bad Boy Dev, and I'll leave a link to that in the description as well. The first task is to set the display mode. The 1602 has two basic communication modes, 8 and 4-bit. This is thanks to the number of pins on the display board itself. It can receive up to 8 bits on 8 individual pins. But we're not using those pins directly, they're proxied to us through I2C, and this leads to a limitation with this particular method. We can only use 4-bit mode. The reason for this is a bit complicated, and John goes into some great detail on his post, so I recommend checking that out for more information. In order to set the display mode, we start out by issuing a command to put it in 8-bit mode. 3 times. Wait, what? Well, as John points out, there are some potential edge cases we want to steer clear of. We may have pause in the middle of sending an instruction, or there may be some weird data we need to clear out when we first start up. By sending this instruction 3 times, we make sure that we are starting out in a known state. We are allowed this one opportunity to use all 8 bits because we're only sending a single instruction. For the rest of our communication, there's a lot more we need to include, as we will soon see. Next up on our list is to tell the display how we want it to appear. We start off by sending some display control commands. According to the datasheet, we can use this to perform several functions, and we want a few features. Most importantly, the screen should be on. We also want the cursor turned on and for it to blink. This is a personal preference, but I like the blinking cursor. It kind of reminds me of my terminal. After we configure the look of the display, it's time to clear out any data that might be there. We send the clear display command and follow that with a command telling the display how to enter new characters. Since we are writing characters in English, we want the cursor to move to the right as it inserts new characters. We do this by sending the entry command and the entry mode right. And now our initialization process is complete. So let's actually show something on the screen. I'd say we've been waiting long enough to see hello world, so let's go with that. Lucky for us, that's as simple as creating a string and sending it character by character. Look at that, a hello world. But hold on just a second. How exactly does just sending a character work with our display? Surely we can't just send an unsigned integer over I2C and expect the display to know what that means. Well, as it so happens, we can do exactly that. Taking a look at the implementation of Rust strings, we can see that the standard library guarantees they're stored in UTF-8 encoding. Now, I'm not going to go into the specifics of various string encodings and their different benefits, but for the purposes of this project, it's enough to know that an encoding is just basically the way that we represent a character in binary. We can see that representation in what's known as a byte map, and Wikipedia has a great one that I'm showing here. Now, it just so happens that this UTF-8 encoding cleverly coincides with the contents of a memory bank inside the display module. As shown in this table from the datasheet, someone took the time to lay out several characters from UTF-8 for our convenience. This is by no means an exhaustive one-to-one, but it's good enough for most messages in English to be received by the screen without any issues whatsoever, and we don't have to do any extra work. Now, as you can see here, there's some special characters we could use, and if we wanted to, it's a little bit more complicated, but we'll see an example of that later on. For now, we can very easily send whatever messages we wish simply by converting each character of a message to an unsigned integer and passing it along to our I2C interface. Okay, all this is well and good, but how are we actually sending this data to our display? To answer that question, let's take a look at a couple of functions we've written. Every time we want to talk to our display, we're actually sending a total of 4 messages. Let's break each of these down. There's going to be a lot more bit manipulation here, so refer to the video I mentioned previously if you're having some issues. Once we have our 2 messages, we then start to add our command bits to those messages. The 1602 has 2 main modes when communicating, and we've seen both of them at this point. These 2 are the command and display modes, and what they do should be pretty self-evident. When we're making changes to how the display works, we use the command mode, and when we want to show a character, we use the display mode. One of these 2 modes is logically ORed with each half of our command. Now that we have the payload broken in half, and a mode attached to each one of them, there's a couple of extra flags that we need to provide to our display. These are going to be the same no matter what, so we'll keep them here and logically OR them with our payload. The first flag is an enable flag, which lets the display know that this data is not to be ignored. The second is a backlight flag and tells the display to keep the backlight on. We could set this to 0 to turn the backlight off, but some characters might be more difficult to see, so we'll leave it the way it is. We send this backlight flag a second time, however. And based on my research and John's blog post, this seems to be required for some displays and not others, but to be honest, it doesn't hurt anything to send it again, even if it's not strictly necessary. Another important factor to point out is that each time we actually send our message, we include the I2C address of our display. As we talked about previously, this is essential to ensure that other I2C devices don't get confused, but we actually get to see it here in action. And as we talked about before in the previous video, even this very simple hello world has a lot of extra things going on under the hood. Now that we are able to write characters to the display, let's actually do something useful. We're going to start out with an infinite loop. Normally this would be a big no-no without some way to break out, but in our case, we need to keep this task going. We are, however, able to keep it from locking up our controller. This is done by listening to the sensor data channel and waiting for it to send a message. Note that this is a little bit different from the sensor task and could potentially run multiple times as we get a bit of data from other sources. It's important to point out in this moment that this is actually one of the very large benefits we receive from using an RTOS. When we await the channel, we're actually telling Embassy that this particular task is paused indefinitely until some condition is met. This allows Embassy to go off and take care of other tasks as necessary, including, notably, the DHT11 sensor task that is supplying the data we want to display. Now, we can assume that we've received a message, so let's display it. First, we need to clear the screen. Since we're updating with a new temperature, we want to get rid of what's currently being shown. After the screen's clear, it's time to construct the data that we want to show. If you're familiar with Rust strings, it should be kind of easy to understand what's happening here, but I'll still give a short explanation just in case. Rust uses 2 different types of strings, known as str and string. A more detailed explanation can be found in the Rust standard library, which I will leave a link to in the description. But the short version is that string can be changed whenever we want, but str cannot. This directly affects where both of these types of strings are stored in memory. Again, I recommend that you read Rust's explanation to get a clearer understanding, but it's important to understand that there are advantages and disadvantages to both of these types. However, this does lead to a limitation. String cannot be used in the embedded world for several reasons, but the most important to us is that we don't really have the concept of a heap, which is where the string would normally be located. To get around this, we can use a crate called heapless, which gives us a little bit of assistance in creating a string we can change later without breaking the rules by specifying a length in memory. Now, why do we need to create a string this way? Well, we could just create several str instances with all the text we want, but it's easier to just do a little string interpolation like we have in normal programming. As with most things, there are multiple approaches, but personally I found this the easiest to implement with no downside. And it will make our job a little bit easier later down the line, so we might as well introduce this concept into our code now. And just like we showed before, once we have our string, we simply send it character by character. I've written a quick function that turns this into chars for us, but it's essentially the same as before, just using generics. I also added a bit of text at the beginning for when the display has finished initializing, but the rest of the Pico hasn't, just so that we have a visual representation of what's going on underneath. But just like that, we have a temperature displayed on the screen. Putting together all the hard work up to this point finally has an effect we can see and show off. Now, I know this is a lot of information, but before we wrap up, I'd like to show off one more feature of the Pico. Buried deep within the datasheet, and the very reason I chose the RP2040, is an analog digital converter, or the ADC peripheral. As discussed in the last video, GPIO can measure the voltage of a pin, but it doesn't give us specific insight into how much voltage is present. This is good for a lot of things, but it can make other things a little difficult, such as a speaker or a microphone. These both rely very heavily on exactly how much voltage is present, and interpreting that is the job of the ADC. However, this actually gives us an additional advantage, a built-in temperature sensor. Through some clever engineering and a little bit of math, we can actually use the ADC in combination with other built-in components to measure temperature based on how much voltage is affected on a specific pin. I do want to point out that the datasheet warns us of a couple of things. First, some calibration is recommended if we expect the sensor to be very accurate. But as we talked about before, we don't really care that much. We just want an ambient air reading, and that can vary a lot even as we move the sensor around the room. Secondly, the source voltage can also affect our readings, which is why calibration or an external voltage reference is recommended. But for our purposes, we really don't need any serious accuracy. Luckily, Embassy has already done most of the work for us. As you can see here, I've set up a very simple task that takes a reading from the ADC VREF pin and passes it along to the sensor data channel that we set up before. And finally, I've added some additional modifications to the display task. We take an average of all the sensor data coming in rather than just displaying whatever the last data point was. This allows us to somewhat balance out and get an average reading of the room that we're in. I've also added a couple of optimizations so that this display is only updating when there's something new, as shown here. While writing to the display like this looks pretty neat, it's kind of an expensive operation in terms of time, and it could potentially jam up our sensor readings, which we would like to prevent. And with that, we wrap up part 2 of this series. While it might not feel like we've actually done a whole lot, it's important to point out that we've covered a lot of detail, and I personally learned a lot while researching all of this over a pretty long period of time. I hope that you've enjoyed the way that I attempted to consolidate and smooth out everything that I've learned along my journey, and I really hope that this inspires you to make something of your own. Thank you very much for sticking around to the end of this video, and since you've made it this far, maybe you'd consider giving it a like, or clicking the subscribe button, or maybe even the notification bell, so you can figure out when I post more videos like this, or see my community posts like this one, where I talk about the PCB and receiving it and the giveaway that I plan on running at the end of this series. I'll be completing 2 Ripple projects and giving them away, and it'll feature this very PCB that I have in my hand. But as usual, I'm very grateful for your support, and just watching the video really means a lot. But I've been Software Engineer Tries, and I'll see you in the next one. Remember how our temperature sensor only used one pin to be able to communicate with our microprocessor? Well, I2C actually has 2 of them. The first one is known as the serial data line, and it's what's responsible for basically the same thing as our temperature sensor, sending ones and zeros. The second line is our Can I help you? Why are you interrupting? That's not nice. That's rude. Yes, it's rude. Hello. Hello. Can I help you? Why are we interrupting? Why are we interrupting?